Alright, hello everybody. It's Sachi back with problem number 3 from this multiple choice physics C mechanics test. So let's dive right in. A particle of mass 2.0 kilograms is moving in the xy plane at a constant speed of 0.8 meters per second in the positive x direction along the line y equals 4 meters. As the particle travels from x equals negative 3 meters to x equals positive 3 meters, the magnitude of its angular momentum with respect to the origin is, then we have A not constant, B 0, C 4.8, D 6.4, and E 8.0. For this problem, it's going to help to make a diagram of what is going on so we can actually visualize it. So, let's make our little... Excuse my terrible handwriting. So let's call this, so this is x, this is y. Let's say and then it's traveling along the line y equals 4 meters, so that's, let's say, about here. So the particle is going like this. It starts here, it goes. That is what the movement of our particle essentially is looking like. And what we're looking at is its angular momentum with respect to the origin. So when I first read this, I did a double take. Why is it asking us for angular momentum when this particle is clearly moving linearly, right? That's a little bit confusing. Let's look at the equations we have for angular momentum. So first we know angular momentum L is equal to mvr sine theta. That's one equation. Another equation we know is L, angular momentum, is equal to moment of inertia times times omega, which is our angular velocity. So let's, just for the sake of this, let's go with this equation. So we also know that V is equal to r omega. So this is linear velocity is equal to radius times angular velocity. So let's isolate theta in terms of V and r. So we can divide by r is equal to V over r. So based on this, we know L is equal to I times V over r. So our velocity here is a constant. We know this here. Our radius, is our radius going to be the same, say, when we're here as to when we're here in terms with respect to the origin? No. These different hypotenuses of this right triangle are going to be different. So our radius is going to be constantly changing. So for this problem, it gives us numbers. We don't even have to use these numbers. We can just think of this conceptually. So we know that V is constant and R is going to be constantly changing. So throughout this line. So based on that, it doesn't even matter what I is. We know that L is going to be changing as we move. It's going to be different here, different here, different here, different here, etc. So we know it's not going to be any one number during this time period. It's not going to be constant because r is changing. This length, the radius between where we are and with respect to the origin, is going to be constantly changing. So, just lost it. Alright, so based on that, we know that the angular momentum here is going to be not constant. It's not zero because there is angular momentum. Even though it is linear, you can also apply the angular momentum model to linear movements. It's not this. And then we know it's not going to be any of these because we know that it's not constant. So this is one of those problems where you don't really use process of elimination. You just kind of once you think of it conceptually, it becomes very clear what the answer is. It's kind of a standout answer. But yeah, that's going to be it. Thank you so much for watching, and make sure to check back in for video number 4.